Note page 213, recapping the idea of entropy, another E word. Entropy is always represented by the capital letter S. So entropy represents the amount of randomness or chaos present in a system. So the basic idea is that if you increase the amount of entropy present in a system, there is an increase in the amount of chaos, therefore a decrease in the order. So be able to define the term entropy, what it represents, but then you might have to look at a system, the reactant side compared to the product side, and identify how the entropy has changed or not changed. So if you think through the process, the phase with the least amount of entropy is a solid, and I'm going to draw that particle diagram, okay, versus the phase with the greatest amount of entropy is something in the gaseous phase where the molecules have no order, not touching, and things of that nature. Now in chemistry we are left with two other phases. Okay, we have our liquid phase versus the aqueous phase, and keeping things simple. If we define something as being in the liquid phase, that means it's a substance, it is pure, and in that container there is only one type of particle. If it's aqueous, okay, it represents a solution. Solutions are mixtures, homogeneous mixtures, and that means there is a solute and solvent present. So that means we have a solute plus a solvent, and they are different types of particles. So that means we have different types of particles. So I'll write that, different types of particles. So I think that because a liquid represents one type of particle, there is probably less chaos in a pure liquid versus a solution. So I'm going to put liquid, and then I'm going to put aqueous solution. So a liquid, its particle diagram needs to be messier, show less order than a solid, but a little bit more togetherness compared to a gas. Right? And outside of chemistry class, like when we see an aqueous solution, such as tap water or Gatorade or things like that, you know, outside of chemistry class we would call it a liquid because the behaviors are pretty similar. So its particle diagram would look pretty much the same. Okay? So number one, compare a reactant's phase to a product's phase. So if you start off with a solid and things end as a gas, there is more chaos. Entropy has increased. If it starts off as a liquid and becomes a solid at the end, look at the particles are more organized, so there's more order, so entropy has decreased. So sometimes you can just look at the phases to determine the change in entropy. Okay? Now, there are cases we come across where all reactants, all products are in the same phase. So in order to determine if the entropy has changed and how it has changed, we need to compare reactant moles to product moles. Just remember, in a balanced reaction, those coefficients represent the number of moles, relative number of moles of each substance present. So the general idea is the side with more moles has more or greater entropy. Now, the last situation that we could come across is that our substances are all in the same phase and we have equal moles. And we're not going to pick this apart at our level of chemistry, so we're going to simply say, based on this data, that there is no change or difference in the entropy comparing reactants to products. So let's take a look here at a couple of examples. So I notice that I have the same two formulas on both sides, but I also notice that there are two different phases. So if I quickly draw, I'm starting off as a solid and I am ending as a liquid. Just looking at those particle diagrams comparing solid to liquid, I would have to say that the entropy increases. Okay? Looking at the next example, I notice that all three substance formulas are in the same phase. So I have all the same phase. So I have to go one step beyond looking at the phases. So I notice that H2 has a coefficient of 2, O2 understood to have a coefficient of 1. So 2 plus 1, I have 3 moles on the reactant side compared to 2 moles on the product side. And remember, they're in the same phase. The side with more moles has more entropy. So, since I'm going from 3 moles to 2 moles, I'm decreasing the number of moles. Must mean I have a decrease in the entropy. Just a picture, okay? Take a look at your picture. Does it look a little bit less ordered on the reactant side or more ordered? So if I'm looking at this picture, it looks to me, I started off with one thing and maybe it got crushed or it fell apart. So it looks like there is less order on the right. So this picture represents an increase in the entropy. Okay. Next to last example, I noticed right away every formula is a gas, so everything is in the same phase. So I need to move on to step 2, and I need to look at total moles on the left to total moles on the right. So I have 2 moles on the left becoming 2 moles on the right. So I have same phase, and I have an equal number of moles of gases, so I would say that there is no change in the entropy. The entropy remains the same. Last example. I notice once again, every substance is a gas, so they are in the same phase. I need to take a look at the total moles on the left compared to the right. So I have 1 mole plus 3 moles gives me 4 moles, and on the right hand side 2 moles. So in this case I'm going from 4 to 2. I'm decreasing the number of moles, therefore decreasing the amount of entropy.